Hello everyone, this is Shivam Modi. So today we will see how to process the biomedical signals like as ECG signals and EMG signals. So in this lecture we will be basically dealing with the ECG signals, that how can we calculate its QRS complex, the P wave, the T wave, and the various things regarding it. So here I have started with it, I have imported the basic libraries, NumPy as NP, Pandas as PD, matplotlib.pyplot as PLT, scipy.io. Actually this file basically is I'm using to load my MATLAB file, because my data set is in the .mat file. Okay, so here you can see that it's in .mat file. So I have imported math, cmath, and matplotlib inline. Okay, so yeah, so if I'll run it, here we go. Oh, so it is taking time. Yeah, now it's completed. Okay, so I have stored that into the mat. So let me show you how the mat looks like. Okay, so this is how my mat file looks like. So we have the concern with this given array. Okay, and rest of the things we'll ignore. Like this is the information where it's got stored and all. Okay, so here we see. So we have seen that how the if you extract this particular column from there, so this is how that looks like. So we'll need just this array, we don't need this information, so we will simply extract this array and we'll leave this data type and all. Okay, so ECG I have stored at mat, and I have provided index as 0. So let me print it out. How does it look like? Okay, okay, so this is my ECG array. So now I can plot it. So plt.figure, fixed size I have mentioned, plot I have given my color as red, and the grid. So here you can see how does it look like. You can estimate the mean of the ECG is going to be like somewhere here. Okay, so that we call as baseline. Okay, this particular noise is coming because of the breathing issue, and if you'll see, if you can zoom it out as a while saving as a figure. Okay, let me tell you, you can save that as an image, and if you'll zoom it out, if you'll zoom it, you will see some, the little variations will be there. So you can filter that out using various techniques, various signal processing techniques. Like you can employ the synchronous averaging. Okay, so let me see. Okay, so here we have visualized it. So we can count the number of peaks here: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so here we go. So our peak count is equal to 13. My switching frequency they have mentioned is 360. So let me tell you. Okay, so switching frequency they have given as 360. So we'll see how much the time covered by this ECG signal. Like there are overall 3600 samples. Okay, so let me print it out. Let me of ECG. Okay, so here you can see there are overall 3600 samples, and the switching frequency is 360. So the total time covered will be my length of ECG signal divided by the switching frequency. So that will come out to be 10 seconds. Okay, I'll have to print that also. Okay, hell, ah, time covered. Okay, so they are and they have taken the 10 seconds. So oh, I have given here also. Okay, so how much one average sample pulse will be taking? Like I'll be saying one pulse is like this to this one. Oh, okay. So I'll be saying it as a one pulse. We will not, we will do the analysis sample wise, not the seconds wise, because there are possibility that 1 second can have more than one cycle also. So it's better to do the analysis sample wise. So with the simply we can see the average sample in one pulse will be len of the ECG and the RP counts. Okay, so here we have seen that there are 13 RP counts. So by that, my average sample, one pulse will have the 276 samples. Okay, so it will come out nearly 276 point something, and we will take the end part of that. So it becomes 276. Okay, so yeah, like I'll be detecting my peaks, like what are the various values of the peaks. Okay, and what are the various indexes at which those peaks are available, right? So as there are 13 peaks, so I have given the range as 1 to 14. P is equals to 0. It is not mandatory to mention the p is equals to 0. It's up to you. If you want to mention it, mention it. If you don't want to mention it, don't mention it. Okay, so I have taken the ECG of 276 into I minus 1 to like this will be doing what, like my ECG array will be uh, searched from 276 into I minus 1 and I into 276. Okay, so let me tell you how does it work. When I is equals to 1, so it will go 0 to 276. When my I goes is equals to suppose 2, so it will be going 276 to uh, 276 into 2, like whatever it is it came. Okay, so and this and that that's how we'll be checking what are the peaks over the peaks available over there. So okay, so here I'll be appending those peaks in my this list, right? Okay, so I have just, let me run it. Okay, so let me print those. So there are the those are the peaks available. There are overall 13 peaks available. So I'll be importing my index, like what are the various indexes at which those peaks are available. And here we can see, like for I is in range 13. Okay, so the same thing, like as I'm detecting my peaks. So here is code, here the two like we'll have to use the loop under loop, that's nested loop, like for I is in range 13, for t is in range 276, like I have taken 276 into I plus 1 into 276. Okay, so wherever my ECG signals at a time instant t will equal to the maximum of I. Okay, so that's the major reason I have given the range as 13, because it will go 0 to 12, and my indexing in max will be followed by 0 to 12 only. That's why I have taken the 13 range over there. And let me run this. Okay, so here I got the indexes at what are the various like index at which the those peaks are available. And here we go. So we will see the what is the difference between R to R wave, R to R point, right? So this is called the QRS complex, Q R S. So how is it? And that's how it goes. So this is the R to R wave. So this is called as heartbeat. Okay, this will basically first come in seconds. So we'll have to convert. This will no, sorry, we will see those in samples, and first then we'll convert it into like seconds, and by the linear operation we will convert that to into the per minutes. Okay, because the heartbeat usually is represented in per minutes, like so let's see. So here we go. So index difference we will see. So 370 minus 77, 663 minus 370, this minus this, and this minus this. So here we see. So we will be storing the index I plus 1 minus index of I, and that will be stored as p, and p will be appended into this list, right? So here we go. So index differences we have got like this. We have converted. Okay. So if you want to calculate the how much samples it is taking, so we'll simply, like, you can see those are not the uniform things that we have got. Okay, so there are some kind of noise present, maybe. So because of that, we will see such kind of differences. Okay, so we'll just take the average of it. Okay, so we have got the average as 290, and this is the uh, like okay, let me tell you, like, how should I explain it? Okay, so this is the time corresponding to 1 second, and this is my heartbeat. So here we have got like 1.2403, right? And we'll have to multiply it by 60 if we want to see it uh, in per minutes. Like, so this is how much my heart beats in per minutes. So here we see it is, my heart is beating 74.418. So it is nearly about like 74 or 75, as we can take. Okay, so here is, I have found the like the average of that. As I have already told you, like, my average will be lying somewhere here. Okay, so here I have calculated the average of my ECG signal and the standard deviation of that. So that's the complete analysis of ECG signal. If you want to know more about this, you can just comment below, and I'll be providing the various details about this data set that I have taken here to analyze my uh, ECG signal. Okay. I hope you best of luck. Do subscribe to the channel if you find it helpful. If you don't even find it helpful, do subscribe it. I'll be keep uploading such videos. Okay. Thank you.